Hey everyone, welcome back. In this video, we'll talk a little bit about how to calculate probabilities. So we will first lay out the sample point method, which is an incredibly useful tool for finding probabilities if there's not too many outcomes. We'll talk about some general rules that can be applied for finding probabilities, namely the addition rule and the complement rule. We'll also talk about some ways to figure out how many ways something can occur if you have a large sample space. So let's get started. First, let's talk about the sample point method. So one simple way to figure out how many outcomes there are and what the probability of each one is with this method. The sample point method has 5 steps. First, we'd like to define the experiment and set up the notation. So just figure out what our experiment actually is. Next, we'll list the simple events associated with the experiment, making up the sample space, here denoted S. 3, we'll assign reasonable probabilities to those sample points in the sample space, making sure the axioms of probability are satisfied. Step 4, we'll define the event of interest as some collection of sample points. And then finally, find the probability of A by summing the probabilities of the sample points. In practice, for simpler problems, these steps all kind of merge together. For more complex problems, we really do want to take the time to go through all 5 of these. So let's start with an example that I like to call the last banana. So picture yourself sitting on a desert island with one other castaway. Beautiful scenery, lots to do. You've really been having a great time, but the food's starting to run out. There was a great banana grove. You guys really enjoyed yourself, but unfortunately now there's one banana left. So you've decided to play for it. And here's the game that you're going to play. You've got 2 die on this desert island. Maybe they're made out of coconut shells. Maybe they washed up with you. But you're each going to roll your die. If you roll a 1, 2, 3, or 4, if that's the highest number between the 2 die that you've rolled, then player 1 gets the last banana. However, if the bigger number out of the 2 die you roll is a 5 or a 6, player 2 gets the last banana. So how would we find the probabilities? Well, first thing we're going to do is figure out what outcomes could happen. So here what I've done is draw a grid of the possible outcomes. So each of these squares in the grid represents an outcome. So for example, right here, this is the event that player 1 rolls a 4, player 2 rolls a 2, the highest number is 4, so player 1 wins. As you can see, this sort of pinkish coral color shows you all of the events in which player 1 would win. The green-blue color represents all of the events in which player 2 would win. Now, it's reasonable to assume that these die are fair, so they're not loaded. That would make all 36 of these outcomes equally likely. So, the probability that player 1 would win the last banana, there are 16 of these events, each with probability 1/36. So we have about a 44% chance that player 1 gets the last banana. Player 2 has the edge in this game. Player 2 wins in 20 of the simple events. So 20 out of 36, player 2 wins 56% of the time. So in the highly unlikely scenario that you find yourself gambling for a banana, be player 2. The next thing I want to talk about is set notation. So how do we represent events overlapping? How do we think about things happening at the same time? There's 4 major symbols that I'll use in this class to help represent different set events. The first here is this union sign. So A union B represents the event that A or B, or both of them, occur. So that is the full union of the 2. The second one, A intersect B, this is the event that both A and B occur. Third one, we'll use a C up in the superscript to indicate the complement, so that is everything not in A. And then finally, this last one here is the subset symbol. So this means that A is a subset or within B. So let S, let our sample space, denote the set of all possible numerical observations for a single toss of a six-sided die. We'll define the event A as rolling a 1 or a 2, B rolling a 1 or a 3, C is a set of even numbers. So let's go through and use this set notation to find these 5. So first, A union B, rolling something that falls into either A or B or both. How those overlap, a 1, 2, or 3. The intersection of A and C, the only even number in A is a 2, so there's just a single outcome. This bar notation is another way to write the complement, so you could write either A superscript C or A with a bar over it. I tend to prefer the C notation for reasons that will become clear later in the semester. That bar has a special meaning in statistics. So A complement, or everything that's not in A, is a 3, 4, 5, or 6. B union C, 1, 2, 3, 4, and 6. That 5 is excluded. And then B intersect C, that is the empty set. There's nothing shared between those two. So now that we've got those ideas of set notation, we can use them to describe compound events a little bit better, and more importantly, list out some of these rules with working with probabilities. So let's start with the addition rule. The probability of the union of two events, so A union B, that can be written as the probability of A plus the probability of B minus the probability of A and B. So we want to subtract away that intersection bit that's in both A and B. We can simplify this a little bit in the case that A and B are mutually exclusive, so if they do not overlap, then the addition rule just becomes the probability of A union B equal to probability of A plus probability of B. So let's take a look at an example. Suppose that 55% of all adults regularly drink coffee, 45% regularly drink carbonated soda, 70% regularly consume at least one of the two. What then is the probability that a randomly selected adult regularly drinks both coffee and soda? So let C represent the coffee drinkers and let S represent the soda drinkers. We know that the probability of C is 0.55, and the probability of S is 0.45, and the probability of at least one, so that's S union C, is 70%. By the addition rule, probability of S union C is equal to the probability of S plus the probability of C plus the probability of S and C. This should be a minus here. Apologies for that typo. Correct on the next line though. So 0.7 is equal to 0.55 plus 0.45 minus S and C, which is the probability we want to find. A little bit of algebra later, we get that the probability of drinking both soda and coffee is 0.25. Now, this can be used to prove an example or prove an inequality in probability called the Bonferroni inequality. And this says that for any two events A and B, the probability of A union B is less than or equal to the probability of A plus the probability of B. Here's the proof of that. So the addition rule states that the probability of A union B is the probability of A plus the probability of B minus the probability of A and B. By the axioms of probability, we know that this intersect here, probability of A and B, must be non-negative. The lowest it can be is 0. In most cases, it will be greater than or equal to 0. So we'll take the union, A union B, as equal to the probability of A plus probability of B minus something that's non-negative. So A union B must be smaller than A plus B. The addition rule can be used to help justify the complement rule of probability. And the complement rule of probability says this: the probability of A is equal to 1 minus the probability of A complement. Here using, again, that bar notation. So think about it this way. What would be the probability of A union A complement? Well, that's going to be the entire sample space. An event is either within A or not. That's it. That's everything that can happen. The intersection of A and A complement is the empty set. Something cannot be in both A and A complement simultaneously. So this should follow then from the addition rule. Back to our example about coffee and soda. What's the probability that a randomly selected adult doesn't regularly drink at least one of these two products? So we found previously, or we were given, the probability that an adult drinks at least one of these two to be 0.7, so S union C. By the complement rule, the complement of S union C, 1 minus 0.7 is 30%. So 30% drink none. This would be the probability that a person drinks neither coffee nor soda. So let's take a look at another example. Suppose that A and B are two events such that the probability of A is 0.6 and the probability of B is 0.3. Is it possible that A intersect B is 0.1? Yes. This satisfies the addition rule. We can plug that in. We get a reasonable probability for A union B, a number between 0 and 1. So yes, this is possible. What would be the smallest possible value for A intersect B? Well, probabilities are capped at 0. So the smallest this could possibly be is 0. Is it possible that A intersect B is 0.7? No. There are a few ways you can show this. You can plug it into the addition rule. You'll get a non-allowable value for the probability of A union B. Here's another way to think about it. The probability of A itself is 0.6. The probability of A intersected with another event cannot possibly be bigger than the probability of A. So no, this is not a valid response. The largest possible value for A intersect B is actually going to be 0.3. It's going to be the probability of B itself, since B is a smaller event in terms of probability. So now that we've got those two rules under our belt, let's think about some ways that we can count up the number of possible options. We're not always going to have situations like the last banana or rolling a die. It becomes difficult to count possibilities very, very quickly. So one way we can count the number of ways that something can occur, or the number of outcomes in a sample space, is with the MN rule. So let's say that we have M events in set A, B1 up through Bn elements or events in set B, and we want to know how many pairs we can get, so how many A-B combinations. Well, the number of pairs we can get is the number of elements in set A, which is M, times the number of elements in set B, which is N. So we can get M times N pairs. This extends, so we can keep multiplying out as we add more elements to our ordered pairs. So suppose we're looking at buying a new car, a 2017 Honda Civic. This comes in 5 different styles with 4 different types of engines, 2 different types of transmissions, and in 8 colors. So how many cars is a dealer going to have to stock if they want to include one for every style, engine, transmission combination? Well, we've got 5 styles times 4 engines times 2 transmissions, so we would need to have 40 cars in stock on the lot to meet all possible options. If we want to have all car colors as well, say at a distribution center, we would take 5 times 4 times 2, now times 8, so we would need 40 times 8 here, or 320 different cars in stock at any given time. Let's take a look at a different example. So let's consider an experiment where we are recording the birthday for each of 20 randomly selected people. We'll make an assumption here. We'll ignore leap years to make our life a little bit easier. This means that there's 365 distinct birthdays that a person can have. Let's find the number of points in the sample space for this experiment. If we assume that each of the possible sets of the birthdays is equally likely, what's the probability that each person in the 20 has a different birthday? because we're looking at birthdays for person 1, person 2, person 3, person 4, we're going to end up using the MN rule to help us out. So this is a pretty famous example. This is called the birthday problem, and we'll work our way up to the 20. So let's start with a small room. We've got 2 people. Here's the probability that those 2 people have a different birthday. It's 364 out of 365. Pretend the person 1's birthday is fixed. In order for there to not be a match, person 2 has to be born on any of those other 365 days. So then the probability that there is a match is 1 out of 365 by the complement rule. Let's go out a little bit more. Say room 3, room size of 4. For size of 3, first person's fixed. Second person has to have any of those 364 other days. Once we know the second person's birthday, person 3 has 363 days left to not get a match. So the probability of different birthdays is 364 times 363 over 365 squared. Keep going for a room size of 4 in general until we get something like this. The probability of at least one match in a room of n people by the complement rule and the MN rule looks like this. 1 minus 365 raised to the n in the denominator, 365 times 364 times 363, and so on. Now, when does this match become likely? When does this become what we would think of as certain? Well, we'll have to plug in some values here. So on your own, I will leave you, and we'll come back to this example in class, to think about what's going to happen with a larger room. What would happen with a room of, say, 20 individuals? The next counting tool that I want to talk about is the permutation rule. So how can we come up with an arrangement of r distinct objects in order? So the number of ways of choosing n distinct objects taken r at a time, if order matters, is a permutation. And we denote this as p superscript n subscript r. The number of ways we can accomplish this is n factorial divided by n minus r, quantity factorial. So here's an example where we might use this rule. We've got 3 employees who will be chosen to win a prize in a raffle without replacement from a bowl containing the name of 30 employees at a small company. So here's the rules. The first person wins $100. Second person wins $50. Third person wins $25. The order in which you are drawn denotes the prize that you're going to receive. So how many possible outcomes are there? Well, we've got 30 employees. We're going to select 3 of them, and the order matters. Which order you get selected in determines whether or not you get a prize. So the number of possible permutations is 30 factorial divided by 30 minus 3 or 27 factorial, or 30 times 29 times 28, which results in 24,360 possible outcomes for this experiment. If you're using, say, a software program called like R, which we'll use later in the semester, you can use the factorial function to calculate these factorials. So that's in fact how I solved this problem. The next tool we can use are combinations. So the number of combinations of n objects, taken r at a time, if order doesn't matter, looks like this. So we write this as n choose r, or we talk about this as n choose r. This is n factorial divided by r factorial times n minus r factorial. Once the order doesn't matter, we have fewer combinations because A, B, C becomes the same as C, B, A, etc. if we don't care about the order. So let's say that a study will be conducted at a hospital to determine the attitudes of nurses toward various administrative procedures. We're going to select 10 nurses to survey out of 90 total that the hospital employs. It doesn't really matter the order in which they complete this survey. Nurse 1 can complete it before nurse 2 or vice versa. Shouldn't make a difference. So this is a combination type problem. So we'll calculate 90 choose 10, which is 90 factorial divided by 10 factorial times 80 factorial. There are roughly 5 times 10 to the 12th different combinations. So there are a lot of ways we could select this sample. In R, we'll calculate these combinations using choose. Let's take a look at another example and start to use some of these properties. A student is going to prepare for an exam by studying a list of 10 problems. This is not a good way to prepare for an exam. She can solve 6 of them. If you're an instructor, this is also not a good way to write an exam. The instructor is selecting 5 problems at random from the 10 on the list. Well, that's the probability that the student can solve all of them. Does the order matter? Probably not. If the student knows how to solve these problems, she should know how to solve them in any order. So we'll use the combination rule. So first we need the number of ways to select the 5 problems at random from a list of 10. So we'll take 10, choose 5. We get 252 for that. Now we need to know how many ways there are to select 5 problems at random from the 6 she can solve. So that is 6 choose 5, or 6. The probability that the student can solve all 5 problems, hopefully this illustrates why this is a bad study procedure, is 6 out of 252, or only about 2.4%. The last thing I want to mention in this video is that we can extend this permutation rule to multiple groups by using what's called partitioning. The number of ways to partition n distinct objects into k distinct groups looks like this, and this should be an equal sign in between the choose notation, so apologies for that. So the number of ways to split into distinct groups is n factorial divided by n1, n2, n1 factorial, n2 factorial, all the way up to nk factorial, where we're splitting into k different groups with these n sub k sample sizes. We will stop here for this video. We'll pick back up with some more probability rules in the next one. Have a great day.